Hey, good afternoon, everyone. It's just now 1 o'clock. We'll wait a couple more minutes here to see if anybody else joins the call, and then we'll get ourselves moving. Thank you so much for joining us today, and I hope everyone's staying safe. We'll get started here in about 2 minutes. So those of you who are new to the DesignSafe webinar series, there's a couple of rules that we kind of set up. If you join in, we suggest that you please mute your microphone, and the presenter will be giving their presentation. And as they're delivering it, if you have any questions, the Zoom sessions do have a built-in chat function. So please use that chat function to ask your questions. There's a couple of us from TACC who are on the call as well, and we will answer those questions, or we will bring those up to the presenter at probably the end of his presentation. Hey everyone, so let's go and get started. It's 1:02, and just so you all know that this presentation will be recorded. We have an archive of all of our presentations for DesignSafe on our DesignSafe channel. You can find that underneath the training option or the training menu in DesignSafe, or to the DesignSafe YouTube channel. All right, so let's go ahead and get started. Everybody, welcome to the DesignSafe webinar series. It's been a couple months since we've actually held one of these. But these are we do these at least 3 or 4 times a semester, focusing on a different aspect of DesignSafe, or a different use case, or a new technology that we would like to share with everybody else. So a little bit about DesignSafe. So today's presentation is understanding and applying machine learning and deep learning. This is part 1 to a 2-part series. Part 2 will be on Monday. So I'm going to go ahead and give a little bit of introduction to DesignSafe itself, and then I'll hand it off to our speaker, Mayar, who will be walking you through the machine learning and deep learning as it applies to the natural hazard community. So my name is Charlie Day. I'm the Director of Training and Professional Development here at the Texas Advanced Computing Center. I'm also the DesignSafe Training Lead. If you have any questions, feel free to email me at charlie@tac.utexas.edu. Also, if you have any use cases that you are currently using DesignSafe for, or a publication, or some data sets that are really interesting that you'd like to share with the rest of the community, please get in touch with me, and we'll put together a webinar where you can talk about your publication, talk about your research, or talk about your data set. And we can make this community grow even farther and further. All right, so DesignSafe, we do have a vision at DesignSafe. We want our cyber infrastructure, we want our portal to be an integral and dynamic part of your research. We want part of your research discovery. Anything new that you find, we would like DesignSafe to play a role in that. DesignSafe is a set of cloud-based tools that support analysis, visualization, and integration of diverse data types. All right. Essentially, what we're saying is you have your own research work, you have your own data sets, you have your own format that you keep your data sets in. We don't want to have you conform to a single method of data curation. So, and essentially all these tools, analysis, visualization, and integration are all part of unlocking what we call big data that you may have heard as a buzzword for the last couple of years. We also want to support the end-to-end research workflow, and we also want to help you develop that end-to-end research workflow. We want to be there with you when you first conceptualize your project, all the way to when you publish your project. And DesignSafe is going to be able to handle all that from point A all the way to point B. And of course, we want to enhance, amplify, and link the capabilities of the other NERI components. All right, NERI has a lot of different components to it, and DesignSafe, we'd like that to kind of help and enhance and amplify the rest of the NERI network. So the way DesignSafe is set is there's the simulation research, the experimental research, the rapid research. All right, so those are essentially the different groups that we have under NERI, right? And they all are producing data, and they're all keeping their data, and we want their data to come to DesignSafe and host it at on our data depot. DesignSafe has what we call the workspace. The workspace is where the tools are available. That's where any custom tool that you guys have developed that you'd like to share. DesignSafe is also going to be where you curate and you publish your data set as well. We understand that data is important, and I'm going to, during this whole introduction talk, I'm going to use the word data a lot, because that is essentially what drives DesignSafe. You have your data set that is very important to you, that could be important to other researchers as well. So DesignSafe is a place where you can host that, you can share that, and other researchers can then cite your data. So the data curation philosophy, all right, we want to allow users to easily store, share, document, and publish their data throughout the life cycle of their project. All right, the data models are going to be flexible and they're interactive, and the curation process is also flexible and interactive. And it allows researchers to decide how to best represent their data set. And our models allow you to consider what's needed of your data to be understandable by an outside user. So if I'm coming in and I'm looking at your data for the very first time, the data model and the curation process should focus in on what's important on your data set. So therefore, I will understand what the story is that you're trying to tell. And of course, you're going to be categorizing your data as well. There's categories essentially user-defined, but some examples that we have is model configuration, sensor info, events, analysis, reporting data, whatnot. So using the data models, the experimental, simulation, other and hybrid, the field reconnaissance work, and social sciences that are now starting to appear on data science, we have different data models set up for these different groups. And of course, we can also sit down with you and develop additional models for your research community. To help you with this, we have our data curator, it's Dr. Maria Estevez. She is very, very good to work with, very knowledgeable in her field, and she holds virtual office hours on DesignSafe every, I believe, every Thursday, or Tuesday or Thursday. Actually, I do have it written in one of these slides. Oh, yeah, there's Tuesday and Thursday at 1 p.m. Maria will have virtual office hours where you can join her at that Zoom address, and she'll be able to help you curate your data. So the curation is actually a rather simple process. You define what your category tree is. So here we have our tree of model configuration, sensor, and event. So that is our tree. And then essentially you assign categories to your data sets, to your files, and say which category those files fall under. And then you publish your project and publish your files. So you create a project, you include your project members on it, and then you publish it. And when you publish it, you have the option of, it actually creates a citable DOI. So once that citation is created and other people use your data, they can then cite your data and essentially give you the credit. So once again, our data models are there to help you curate and publish your data. And every Tuesday and Thursday, Maria has the online DesignSafe virtual office hours. So getting your data to DesignSafe, there are multiple methods. You can upload directly through the data depot and through the Jupyter notebooks. There are some limitations on that, of course. You can also link up Jupyter or DesignSafe to your Box account or Dropbox or Google Drive, and you can sync your folders. You upload them to your desktop folder in Box, for example, and then you have to manually sync it into DesignSafe. If you have a large amount of data that you're trying to bring in, Globus is a great tool to be able to manage that. So if you have a large number of files and folders and a large size of files, Globus is great. We also give you a command line interface where you can upload your files and folders using a command line tool like rsync or scp. We do have some data transfer guides available to you at these links that are listed. And there's also the Globus data transfer guide as well. Globus does have a couple little nuances you have to set up. So I do suggest, if you want to use Globus, to familiarize yourself with that transfer guide. And it should be a piece of cake then. All right, so make your data count. We want you to publish your data, and we want to give you allow you the ability to cite your data, and then be able to expand your data set with other users, and other users be able to expand your data set on how they use it. The entire thing is your data is what makes DesignSafe so successful. So the more data that you bring to it, the greater the community can grow. All right, so with that, let me go ahead and introduce MyR. So today's topic is understanding and applying machine learning and deep learning. And this, like I said, part one of a two-part webinar series. So we've discovered that machine learning is an application of artificial intelligence that provides systems the ability to automatically learn patterns from previously documented data, which is why data is so important. And of course, recently, many researchers have utilized these techniques to facilitate tasks in visualizing, analyzing, and predicting natural hazards. So what we're trying to do is get your data, learn from your data, and then be able to predict future natural hazards. So this is the first session of a two-part webinar series. What essentially we're going to do here is MyR is going to walk you through some conventional machine learning algorithms, for example, as he's got listed, decision tree, random forests, and how they apply to the natural hazard domain. We'll also explore and introduce these concepts to you if you've never actually used them before. And the webinar will essentially go through an overview of the basic steps needed to build these machine learning models, and then showcase these in the context of natural hazards. We will be using DesignSafe Jupyter Hub and classification algorithms that are been employed to predict the performance of residential buildings using reconnaissance data from Hurricane Harvey that we have stored on DesignSafe. So MyR is a PhD. MyR Sharif is a research associate here at TACC. He's been with us for a couple years now, and I worked with him very closely. He has his bachelor's in mining engineering from University of Tehran, and his master's and PhD in civil engineering from Oregon State University. And his research focuses are on regional landslides and lateral spread of hazard mapping. He has given lots of webinars through us before. I ask that you also go visit our DesignSafe YouTube channel, and some of his other webinars are posted there. All right, so without any ado, let me introduce MyR to you. And MyR, I'm going to stop sharing now and let you pick up the share from your screen.
Okay, thank you, Charlie.
And thanks, MyR.
Okay, so Charlie, can you see my screen?
Yes, I can. You can see your screen.
Very well. Good afternoon, everybody. My name is MyR Sharif Mood, and I am a research associate at Texas Advanced Computing Center. And I'm working mainly on DesignSafe cyber infrastructure project. My background is in civil engineering. And today I will be discussing a topic of understanding and applying conventional machine learning algorithms in the natural hazard domain. So I will roughly present about like an hour, and then we can kind of like use the rest of the time to for those who would be interested to actually went through the example and run the notebook themselves, we would be here to support for that as well. The agenda for my presentation is to discuss the artificial intelligence, machine learning, and deep learning landscape and how these techniques are used in natural hazard. I will introduce an example problem on structures damage classification after Hurricane Harvey. And I will discuss software supports available at DesignSafe, which includes Jupyter notebooks and machine learning packages. I will also provide some basic level intuitions for some of the most common conventional algorithms that are used in natural hazard domain, and we'll go through the required steps that needs to be completed before one can actually build and train their machine learning models. And also I will conclude by demonstrating the Jupyter notebooks that apply some of these algorithms to our to a damage classification, building damage classification problem. Artificial intelligence, machine learning, and deep learning, they are sometimes these terms are used like interchangeably. However, informal, they have different definitions. So in high level, usually deep learning contains the neural networks, algorithm types that are essentially a subset of machine learning in general. And machine learning itself is a subset of the artificial intelligence and the knowledge bases in that area. So there are enormous amount of hype around these terms these days, but really there is essentially nothing magical about these techniques and how we actually compute them. Most of these concepts in machine learning and in neural networks have been around for decades. And however, the big difference is that during this past 10 years, we now have actual computation power to get actually something interesting from these results in comparison to old days. You can for every thing that you want to use, essentially you can think of machine learning and deep learning methods to be simply called as statistical models of a system. Rather than what we usually do in engineering domain to create physics-based model. However, with any statistical model, there are some questions that appear. First is that if statistics can outperform the predictions that might arise from other models, do we have enough good data and stored already that can be used to build these good statistics? And what does your model do when it sees something that it has never seen before? So these are type of things that you will have to consider before you actually choose one of these statistical models or build upon one of these previously created engineering frameworks. So for all intents and purposes, machine learning and deep learning is essentially just an advanced curve fitting, but it's essentially more than just a straight lines that we generally see in engineering papers. So machine learning has various applications in all aspects of natural hazard, from predicting natural disasters such as earthquake, flood, and hurricanes to the building damage classifications, landslide and soil liquefaction susceptibilities. Researchers in natural hazard are using these machine learnings on various problems. However, the big caveat is that in order for these statistical models to actually result in good outputs, you will need to have comprehensive and enough good data that are stored in a correct structured format that you will be able to feed into your model. So in that sense, I'm here in DesignSafe, we have a variety of data sets, as Charlie mentioned as well, which are published by different like natural hazard researchers, whether it's in simulation research or experimental or field reconnaissance. So in this particular webinar example, I will provide I have selected one of the field reconnaissance data that are published in DesignSafe by David Roush. That collected a door-to-door wind-induced residential building damage in Texas after Hurricane Harvey. The data set is assessment of building performances. So as you can see, here are the landing pages of the published projects. There are two projects, one which is published by David, and then there is another one which is a supplement data to the previous project. So the data set is an assessment of building performances, and it is structured in a spreadsheet format. They have used Fulcrum application in their field reconnaissance mission. And they stored a variety of properties for each single house, as well as they also came up with the overall building conditions after the Hurricane Harvey. They also took a lot of pictures at each of single houses, and essentially these data sets are stored row by row in a structured format. Which can be used for further analysis. Essentially, each row in this data set is a building, and various columns are describing the overall performance. Like one particular, for example, column is describing the overall performance of the house, and also the other columns are the various properties of the house, like the age of the house, the roof cover, roof shape, and also one particular field is the photos and names that are took from that particular house. So as with any real data set, a lot of data cleaning has to be done and completed as a pre-processing step before one can actually be able to start feeding their machine learning models to the data. So according to Forbes, data scientists usually spend 60% of their time just cleaning and organizing their data. So that sort of call for why this particular steps is a very important one. It essentially involves feature engineering, which is the process of selecting and handling parameters that are relevant to your target variable. In this case, we are trying to predict the overall building condition, like the performance of their residential house. So looking through the data set, we'll think like some columns that might be explanatory for them. So we'll choose them and we'll kind of like go through them. Some of these columns might be like categorical, so you will need to handle those as a part of your pre-processing. You might have a lot of like real data sets might come from multiple sources, and you will have to make sure that these are corresponding to each other correctly. So like in my case, when I was trying to go through this example, I've seen that like from one data set, you'll have like stated that the roof cover is like some specific parameter, and that same parameter was stated in another name, which was essentially a similar thing, but with another formatted mentioned. So you will have to go through them through your script and start seeing patterns and clean your data set. There are examples like in this particular data set I've seen like first floor elevation that they had large missing values. So you will have, sometimes you will, there are columns that are interesting to your problem, but you don't have enough data, or there are tons of missing values in there. So in that case, you may end up dropping that data point in particular, or deciding just to remove that feature altogether. Another, or maybe a better way to handle missing values is to actually perform a process which is called imputation, which has like multiple approaches. First would be to derive the value from related columns that are correlated to that particular feature. Next would be to find the most common non-value from the same feature and assign that, maybe an average or some sort of a mode or some other statistics that can fill those values. You can also use a placeholder for missing values. However, the best, I guess, technique would be to augmenting the factual data using an external source. And if the funding allows, you can actually go further and collect more data, which in case of perishable data sets after a natural hazard, it might not be feasible, even with funding. So essentially, yeah, that's a very big important very important steps before one can proceed with its modeling. So once again, in our example, we are going to fit decision tree and random forest machine learning algorithms to classify the performance of buildings given their properties. The models that will determine whether a house given certain features will be classified as, the models will be determined, essentially will determine whether the house will be damaged or it will be categorized as no damage after creation of the model. I have used the scikit-learn library in a Python notebook that runs in a Jupyter Hub from inside DesignSafe. So for our problem, I ended up selecting our dependent variable y to be equal to be the overall building condition of the house. While the actual data set was had a lot of variability in this particular variable, which was defined from 0 being no damage, and then 4 to be fully damaged, and then it had other categories as well as minor, moderate, and highly damaged. I ended up just selecting two to perform a binary classification for this particular example, just to have this as a proof of concept. That variability dependent variable also plays a very important role in terms of how your model will predict. The input feature matrix and essentially the explanatory variables that I have selected from the data set was the age of the building, the maximum wind speed from hurricane, number of stories, roof shape, roof cover, wall cladding, and structural framing system. So the DesignSafe supports softwares for machine learning. Usually there is nothing that avoids you to produce your custom codes for any algorithms that you would want to apply. However, obviously the easiest way to get these and the fastest way to get and maybe the more efficient way is to use the common frameworks that are already developed. So for machine learning, scikit-learn library, Keras, TensorFlow are like major Python libraries that can be used, and essentially you can take advantage of those in your modeling. Also, Pandas is a great data processing framework that is used in Python. The typical language of choice is usually Python, and the best way to work interactively with Python is through the Jupyter notebooks. You can launch Jupyter from within DesignSafe. I particularly, as I mentioned, I have used scikit-learn library. It's a simple and efficient tool for predictive data analysis. It's accessible to everyone, reusable in various contexts. It builds on top of NumPy, SciPy, and Matplotlib essential Python libraries. And it's, of course, open source, which makes it great to work with. So introduction, I will now move on to provide an introduction to our conventional machine learning, some of the conventional machine learning algorithms. So in this particular session, I will focus on supervised learning, but but in generally, machine learning has three different types of, three different domains. The first one is the supervised learning, which essentially tries to learn a function to map an output, to map an input to an output. So technically in the supervised learning, you split your data set, which has already, with a known ground truth, we'll split it into a training data set, which usually is like 80% or something like that. And then you have set aside a 20% for test data set. So you have your training data with desired outputs with the ground truth. And if these outputs, if the thing that you are trying to predict are categorical or binary, then you are trying to make a classification, like whether it's going to be green or blue. And then if the outputs are numerical, then you're dealing with a regression problem. So for example, in terms of natural hazard, if you consider slope variable, geology, like vegetation index and depth to groundwater, for example, to predict whether a region is susceptible to landslide or not, we are dealing with a supervised learning classification problem. However, on the other hand, you may want to try to predict the actual lateral spreading values given like some explanatory variables. In this case, it could be SPT or CPT parameters like thickness of liquefiable layer, slope, or like free face values. Then in that case, you may end up with a problem of a supervised learning for a regression problem. Next, in there is the unsupervised learning, is where you don't have any particular labeling or categories, and you are trying to find previously unknown patterns, and you are trying to essentially group your data sets into subcategories without knowing anything beforehand about the data. One of the most famous methods of these unsupervised learnings are k-means clustering. And then there is reinforced learning, which which essentially sets of learning policies over time while interacting with an unknown environment. So with that, I will focus on some of the most commonly used machine learning algorithms in natural hazards. Linear regression, logistic regression, k-nearest neighbor, decision tree, and random forest are among these techniques. And I will now go through the intuition behind these algorithms. It's going to be a little bit of a high-level intuition for these models. Just you essentially will need to go through these in much more detail if you further wanted to apply these in your own research. So the very first one, which I assume that most of you are already familiar with, is the multiple linear regression. This essentially tries to learn a function fx to predict the target variable y given a training data set. Its objective is to minimize the residual sum of squared. So as you can see, we are trying to feed a line to our data set. In this case, it's just a one-dimension feature x, and you're trying to feed a line. This is called essentially simple linear regression. And your model is predicting y hat, and the actual value in the training data set is like y. And then your objective function is to minimize this for all of the data sets. So it's trying to find the best fit line that goes through this. So with that, this particular algorithm it's called a parametric machine learning algorithm, since it's going to result in a closed form mathematical function that best describes the pattern seen in the training data. So once again, it's trying to optimize and find the line. But however, remember that this is just not simply, in terms of a one dimension, it's a line. But if you have your problem that has multiple, like in this case, x1 through xn, multiple dimensions, you will have like a hyperplane that is applying in hyperspace. So now that we already discussed how to handle these type of data sets, like in terms of like a 1D, we know that we need to fit a line, or in higher dimensions, fit a plane to data. But what if now our dependent variable is binary and is it categorical? Like, and the data set, it's either 1 or 0 according to its feature. So can we just fit a line to this as well and think about it, like whether it's gonna be okay? So let's just think about this in terms of an example, like a verbal example. In this case, let's assume that y is the landslide susceptibility. Whether it's going to be landslide susceptible to be in case of a y equals 0, and then y equals 1 in term being not susceptible. So the feature x could be soil shear strength in this case, for example, and then you will in the area in between, you can think about it that it sort of makes sense. So for a shear strength, soil shear strength that is in lower values, you will have closer. You are predicting closer to a target variable being landslide susceptible, and higher means like closer to be not being susceptible as the soil is going to get stronger. But the thing is that the areas outside of these regions doesn't make sense much. So we cannot say that it's higher than actually being susceptible to the region being actually susceptible to landslide or not being susceptible. So it's maybe better to fit something like this instead of a line. And that sort of calls for the intuition behind the logistic regression. So we'll take our line and we apply a logistic function, which in this case was a sigmoid function. It's a transformation function. And it's now this time it's going to fit a curve to our data set. And as you can see, in this sense, it's converting the target variable from being categorical to a probability. So now you will, for any particular soil shear strength, for example, in this case of a one dimension, you are having a probability of the region being landslide susceptible or not. So that sort of this describes the intuition behind the logistic regression. It essentially, you can see that in this transformation, you now have the probabilities. And if you actually want to predict the categories, whether, for example, whether it's going to be landslide susceptible or not, you will select a threshold probability depending on your problem. Like it could be 50% or something that is defined based on the science domain. And then you will predict your y according to the probability and the threshold. If it's going to be higher, you will predict it to be 1, and if it's lower, you will predict it to be 0. Next in line is our simple algorithm, I guess, very useful though, the k-nearest neighbor. It's essentially, it's a very simple algorithm. Let's assume a problem where we have two classes of categories, red dots, which are highly damaged buildings in this case, for example, and then green dots, which are no damaged buildings. And X1 is our feature, our first feature, which is the age of the building, for example, and then X2 is our second feature, which is the hurricane wind speed, for example. We have our new data point and we want to know whether it's going to be assigned to the category of damaged or to the category that is that means no damage. So for the algorithm goes through this. You will have to select a number k, which in this case I've selected 5, and find the five closest neighbors to that particular new data point. So that applies based on either Euclidean distance or any other metrics of distance that you will select based off of your problem. Once you once you selected those nearest neighbors, you will count the number of data points that are in each category, and then assign the data to the category where you counted the most neighbors. In this case, it's 3 categories of damaged, so your data points, and it's higher than 2, so your data point will be assigned to that. So next algorithm is decision tree. It's a non-parametric method, and as you can see, it deals with the data sets that are not linearly separable. The model is constructed based on observed data. The goal of decision tree is to make the optimal choice to split the data set into subcategories where the categories are where the categories are measured whether to be pure or or the split gives you higher information gain. I won't go through the mathematics and details behind the information gain in entropy and like Gini index idea here, but essentially take note that you will want to make the splits that gives you that separates your data set into categories, into subcategories of that are separated best. So in this example, for example, let's assume an electrical outlet inundation prediction. We want to know if after a storm surge and like a flooding situation, we will have our first floor electrical outlet be inundated or not. And our X1 feature is the first floor elevation, and our X2 is like the precipitation or rainfall. So our first split happens at like 60, and that essentially separates our data set into sub regions. For the areas that are greater than 60 in terms of precipitation, we are separating again at first floor elevation 1. So all the areas that has low first floor elevation and has higher precipitation values, they will be the model will assign them in a category of inundated, and no for the rest of them. Same thing applies when we are building our tree from top-down method. The split, the third split will happen at the first floor elevation at 4. We'll continue this, so on, so that we have our perfect splitting of our data set. So remember that it's not always going to be this, like this is obviously just a simple example of what we are trying to show, the intuition of the decision tree classification. In the real data sets, you will, if you try to go, like if you try to build your decision tree all the way into much deep layers of splits, it's going to end up in what we call overfeeding to the training data, and it's not going to work well in the data sets that it has not, your model has not seen yet. So after the decision tree has been created for your classification problem, it is essentially created these sub-regions. So in this case of a 2D, you are seeing it regions, but it's going to be hyperspace in multiple dimensions. And for any new data that comes in one of these regions, it will try to look for it based on the features that it has, the region that it is in there, and it computes the category that it needs to be assigned based off of that. So now that we know how that works, we can sort of use the ensemble method called random forest algorithm. In random forest algorithm, we are essentially selecting k random data points from the training data set. This happens with replacements, and we build a decision tree to these subset of data points. And we will repeat this analysis for n number of trees. So if you repeat this like for 20 times, you will end up with 20 different decision trees. And in your last step, for any new data point, you will make each of these created trees predict the category to which your data belongs to, and then assign that new data point to the category that wins the majority vote. So I want to specify two specific things that are very important with any machine learning models. The first one is the bias of model, which is essentially the difference between the average prediction of our model and the correct value that we are trying to predict. So essentially is that if our model is correct or not when compared to to the ground truth. If you have a high bias model, your model is just essentially too simple, and that means that it's most likely gonna underfit. It's in an underfitting situation. Whereas in the other case, there is other parameter called variance, and it is a variability of model prediction for a given data point. So high variance pays a lot of attention to the training data, on the other hand, and any outlier that is in the data set. And in that case, it's not going to generalize to the data set that it didn't see, that it has not yet seen. So for complex models with high variance, you're probably going to end up with an overfitting situation. In these type of situations, which is really something that we want to avoid, we have high training accuracy data, but we have low performance in the data sets that our model has not yet seen. Essentially, this is a trade-off that we need to be aware of, and we need to find a good balance between the overfitting and underfitting the data to find a good balance with low bias and acceptable variance. So with that, now we need to evaluate the performance of our models. We want, depending on the nature of our models, we have different methods of evaluations. If it is a classification problem, our model will be evaluated based off of what we call confusion matrix. Confusion matrix is essentially looking like this for a binary class. For a binary classification. So essentially this here tells that the true positive is essentially where our actual values were positives and we predicted values correctly to be positive as well. False negative is the case where the ground truth was positive, but our model mistakenly predicted that to be negative. False positive is the case, is the bad case of where the actual value is negative, but we mistakenly predicted that to be positive. And last one is the true negative, which is the case where the ground truth is negative and we correctly predicted that our model correctly predicted that to be negative. So as you can see, we want the elements in our main diagonal to be higher than the other ones. So, and that sort of explains what the accuracy comes from. Usually you will select, sum the total number of true positives and true negatives divided by the total number of predictions made by your model. There are other metrics as well, in this case, like recall and precisions, which you can also use for evaluating your models, especially when your data set is unbalanced. But in the case of a regression problem, usually there are other metrics that you will have to use. The first one is the coefficient of determination, which is R squared. Mean squared error and mean absolute error are the next two parameters that are used in evaluation of the regression problem. For example, mean absolute error, assuming that these are the test data and this is our model, mean absolute error is the difference between our predicted value from our model and the actual test ground truth value from the test data set. So you will take an average of those and you will see that if your data set is actually working by your standards or not. So with that, now let's continue by going through our example. Remember, we will open a Python notebook and try to fit decision tree and random forest classifiers to our Hurricane Harvey dataset to predict the performance of our buildings, to be classifying them whether to be it's going to be either destroyed or no damage. Here are there are essentially steps that we need to take to build our classification model. The first one is to import libraries from like scikit-learn, NumPy, Pandas, Matplotlib, and these essentially allows us later to bring our data set into the Pandas data frame and being able to go through the data set, create the histograms of the various columns and see how they will correlate it with one another. Then we'll continue with cleaning the data set and missing the data, handling missing data. In this particular case, I have cleaned the data set previously. It took a lot of time, but I ended up like providing data set in the community data for you guys to go through it for a clean data set. Next, we will need to handle categorical data sets and features, feature scaling if your model needs that. I will go through these one by one. Your data set needs to be split to training and test. And you fit your model to train data set. And then you're ready to fit your model to train data set and compute the model performance on the test data set. So the first step was importing the libraries. As I mentioned, I have created this pickle file, which can be used. We can use read pickle method in the pandas library to bring this data set bring your clean data set as a pandas data frame, which I have called Harvey. And then you will need to create your matrix of features X and the dependent variable Y. I've selected iLock method that is available for pandas data frames to select the matrix of features X and then label Y, which is the overall building condition. Next, I had to handle the categorical variables. So in this case, we needed to focus on the features of this problem that, in this case, it was like house's roof shape. Using label encoders, we need to convert these string type of data set values into something that our model can work with. Essentially, this goes for encoding, and this calls, and you can import the label encoder to convert these string values to encoded values. However, if your model is based on Euclidean distance, it's going to put more weight to something like this. In this case, it's going to put more weight to gable type of roof shapes for some reason, because the encoded value is 3 and it's just simply higher than 2 and 1. So you want to avoid that, and for that you will have to create dummy variables in order to avoid such problems. That usually applies with one hot encoder, and it allows to, you can use that in order to avoid witnessing some of these issues. You will now be able to build your training and test data sets using the train test split, which can be imported from model selection from scikit-learn library. Usually this will, that it needs, it's the matrix of features, the target variable Y. You will pass in the test size that you want. In this case, I've selected 25% of our data set, and a random seed number that you can put in order to get repeated results if you want. Next is the feature scaling. If your model is based on Euclidean distance, you will have to scale your matrix of features, so the model do not pay a lot of weight to a feature which is in order of 10,000s compared to another feature which is in the order of tens. So a standard scaler is used to feed to train data and transform all features. So essentially you will create a standard scalar object. You will feed them to the extent of your trained data set and transform your trained data set. And now you will have to use that created object to transform your test data set as well. This particular process is not needed because in our example, because we are feeding decision tree and random forest, which are both based on, which are both not based on Euclidean distance. And then now we are ready to actually feed our models. From the scikit-learn tree, you can import the decision tree classifier object. There are tons of variables that you can find in there in the scikit-learn documentation that goes into introducing the decision tree classifier. What I have used is just the criterion to be selected as entropy, which essentially means that our decision tree is going to be built based on information gain and not the Gini index. You can change these, and these are essentially hyperparameters that you can tune later to get your get the best out from the classifier that you are going to build. Once your object is created, you will need to feed it to the trained data set using the ground truth of the training data. And similarly, you will select the random forest classifier from ensemble and pass in its own inputs. So in this case, I'm passing number of estimators for the random forest classifier. You could, like, I'm essentially creating 100 number of trees, and I'm selecting each of those trees to be split optimized based on the criterion of entropy. And I can feed another classifier to my training data set and train it based on the ground truth of the training data set. Once those models are ready, I can use either of those classifiers to predict my test results, my test data points, and predict my values. Once I have my predictions, now I'm ready to create my confusion matrix and essentially report and evaluate my model performance. As with any model, you will need to know what that particular model is placing more weight on in terms of classifying. So for each model created, you can report the features that are most important. And it turns out that for our decision tree, for example, maximum window speed and age of the building are the two most important features that our decision tree classifier is using in order to classify. So with that, I will now go through some of these slides that explains how we can actually use the Jupyter Hub in DesignSafe for this purpose. I have put these slides in here just for those of you who might want to refer to these later to be able to go through this example. So you will end up, you can log into DesignSafe, go to Research Workbench and then Data Depot. In the community data under Machine Learning Bootcamp, you can click on Community Data under Machine Learning Bootcamp. You will have your notebook and the data sets that we have. All you need to copy at this point is the notebook itself. You will click on Notebook and then you will select Copy, select My Data here, and you copy to your My Data because community data is a read-only space and you will have to walk through it in your own personal space, which is My Data. And then you click on the copy to your username. Now you can go to Research Workbench again, and this time you will click on Workspace, which is essentially the place where all of our DesignSafe applications resides. In the data processing, there is Jupyter application, which you can select. And then you will have to select the version of the Jupyter. For the purpose of this particular webinar, we are using the main Jupyter Hub, not the TensorFlow workshop. which will be the one that you use on Monday for in our next part that actually runs on Frontera GPUs, one of the TACC systems. So after you select the Jupyter, you will click launch and it will start your Jupyter Hub server. You may need to log in if you haven't before in here again using your DesignSafe account. And you will have to click on My Data and find the copied notebook that you just brought from community data. So with that, let me go through this as a live example. So hopefully you guys can still see my screen. So here, I'm in DesignSafe website. I have already logged in. Inside the research workbench, I'll go to Data Depot, and under Community Data, there is this Machine Learning Bootcamp, and the particular folder that we want to focus is the Building Performance Classification. I have provided the data sets as well as the notebook and the slides of our presentation. So you can select this notebook and then click copy my data. And you can now click copy to your username. So it may take a few seconds before it's gonna copy. You'll have a data was copied thing that you will see there. Now we'll go back, select the research workbench, and this time we'll go to workspace. This is where all of our applications reside. As you can see, a lot of simulation applications as well as visualization applications that we have in the portal. But the one that we are interested in is the data processing for, and that's Jupyter that we select. From the drop-down, remember to select the Jupyter in this time, and you will just click launch. So as you can see, it's gonna ask to sign into Jupyter once again using your DesignSafe account. You will have to log in. This process might take a little bit of a time, and now you will have to start your server in the Jupyter Hub. So this essentially is trying to create a container that works for the Jupyter Hub, and it's trying to bring all of your My Data and My Projects data sets that you already have in DesignSafe to be able to now work with. So now I select My Data, and as you can see, I find my notebook that I just copied. So I click on that, and it opens the Jupyter notebook that we are gonna use for our classification problem. So I'm gonna go through this line by line, but I'm just gonna give the overview of what this Jupyter notebook is trying to do. And we already discussed a lot of the steps already. So we'll just gonna go through this and see how it's gonna turn out. Usually the way that a little bit of information about the Jupyter notebooks, if you are not already familiar with, you have these cells that you write your scripts in Python, and in this case, it's Python 3 notebook that I have created. And you will be able to run each of these cells separately from one another. So in this case, I'm using this cell, and I go cell and then run cell. So this star essentially means that it's running, and then once that you have your number here, it essentially means that that particular cell has been run as one. Either you can use cell and run cell, or then you can use control and enter to run your cell. So the second one is to import our data set. If I comment this, this particular one is trying to read our data sets that are available in the community data path, and then it's trying to display the histogram numbers of our overall building conditions. So in terms of a tree in terms of a tree case, I have two data sets, one tree groups and one two groups. I'm going to go with the two groups first. So actually, yeah, let's just go with the two groups. And then if I create that, you can see that there are 288 residential buildings that are not damaged, and then nearly 200 buildings that are fully damaged from our data set. Now, using the tail method, I can go through the like find like the last 15 rows of the data frame that the pandas data frame that we have. As I said, this is the clean data set. It has all of our data sets, all of our features that we are interested, and also our target variable overall building condition. So we need to next build matrix of features, which is X. We start going by using the iLock. As you can see, this usually start in Python. Usually the indices starts at 0. For the overall building condition, we'll select all of the rows and the column 0, and for every other columns are features that are stored in the matrix of feature X. So I will run that. And now we'll need to, as you can see in our data frame, roof shape, roof cover, wall cladding, and structural framing systems are in categorical format. So we'll need to transfer these, transform these into encoded values. And I'm not using the one-hot encoder to create dummy variables. Once again, this is because the models that we are using is not based on Euclidean distance, so it should be all right to just use the label encoder to turn these into digit numbers that models can work with. I've run this, and essentially now the matrix of features will be having values instead of these string and text values. Now we are ready to split our data set to train and tests. As we discussed before, we have selected 25%. It results in creation of the X training, X test, Y training, and Y test. I'm not applying the feature scaling because it's not needed for our classifiers. Here, I'm just defining some class names just for our confusion matrix to look nice. Yeah, so now we are ready to apply our decision tree classifier and predict test set and report our model performance. So I've already gone through the lines of the codes that we've seen in the slides. So once again, we are using entropy. We are feeding our training data set, and we are trying to predict the test results. And here it's all just trying to call a function of the confusion matrix to build the confusion matrix that looks nice, and it reports the decision tree accuracy of our classification for the training for the test data set. As you can see, we have 61 number of correct predictions of no damage, and then 41 correct predictions of destroyed houses where in fact they were destroyed. Now we will want to see if we can actually if the random forest classifier actually is an ensemble method, and technically it should perform a little bit better than decision tree algorithms. So I'm going to run the similar approach this time from the ensemble method scikit-learn. I'm applying the random forest classifier, and I applied that to our problem, and it turns out that we were able to increase our accuracy for about like 3%. Keep in mind that this data set that we are working with is a classroom size example. It's not a, like, still I have selected rows and a number of data sets that we have is limited. So it still needs, in order for this to actually being able to have a very good classifier, you will need to end up making larger data points, as well as making hyperparameter tuning in order to have a decent classifier that you will be able to actually use in your research. So the next is the feature importance. We would like to know for our random forest classifier, what are the features that are most important to our to the classifier. And it turns out that the age and the maximum wind speed are once again the two most important variables that are used in classifying the test results. So with that, I would like to get back to the slides and provide a little bit of a summary and conclusion for what I went through. So remember that the data is a new source of power in our research. We can combine engineering frameworks with models learned from data to improve quality of predictions. DesignSafe data depot, as we mentioned, contains a variety of published natural hazard data, whether it is in experimental, simulation, or field reconnaissance research. Remember that data cleaning is a vital and necessary pre-processing step to make the data structured in a way that it is ready for our modeling through machine learning and statistical analysis. Here at DesignSafe, we offer software and hardware supports and for natural hazard research in artificial intelligence. Feel free to contact us with any questions or inquiries that you may have in regards to your computational needs. I have placed the slides, notebook, and the data sets that we have that I've used in this webinar, and it can be found under community data under Machine Learning Bootcamp. Also, last but not least, remember to check out our part 2 session of our AI webinar, which focuses on the same data set, but the images of this particular data set. And our speaker will go through the deep learning and convolutional neural network that applies for an image classification problem, which will happen on Monday. So stay tuned for that as well. With that, I would like to open this to any questions or inquiries. And also in future, if you have any particular question, please submit a ticket in DesignSafe or contact me at my email address, which is mmood@tac.utexas.edu. So with that, I will give this back to Charlie.
Awesome. Thank you very much, Mayar. That was very cool. I really enjoyed that a lot. That was great. Hey, if anybody would like, these slides and the video will also be published to our DesignSafe Learning Center. If you go to the Learning Center, go to Education and Training, it'll be posted there in the archive. You can also watch this video. It'll probably be posted to our YouTube channel next week if you want to watch it again. Mayar has already published his slides and his published notebook on community data in DesignSafe as well, so you can always review that again if you need to. If there are any questions, feel free to hit us up. Feel free to hit us up on either email, training@designsafe-ci.org, or fill out submit a ticket, and then Mayar and I can look at those. And there, of course, don't forget we also have the Slack channel as well that's available to you guys, the general channel for any conversations you might like to have, or if you want to direct message Mayar or myself. Special thanks to Mayar. Thank you so much for taking the time and going through your research with us and showing how machine learning can be applied to the natural hazards community. Also, a big thanks to our PI, Ellen Rathje, our co-PIs, Tim Cockrell, Jamie Paget, Dan Stanzione, our web developer, and our webmaster, Hedda, a manager of whose team actually built the portal for us is Tracy Brown. And then, of course, Jason with the user services team and our project manager, Natalie. If you have any questions, feel free to hit us up anytime. And once again, just want to remind you, next week on Monday will be the part 2 of this 2-part webinar from 1 o'clock Central Time. All right. If there are no questions, if there are any questions, feel free to ask them on the Zoom chat. If not, we'll go and end the Zoom session now. And if there are any further, if you have any questions later, hit us up on Slack. All right. Thank you very much, guys. I hope everybody has a great weekend and stay safe.
Okay, I've seen some questions that are arising here in the chat window. Once again, before I go through these, feel free to try this yourself. We will going to be staying for like maybe next 5 to 10 minutes in order to provide support for anyone who wants to go through the actual hands-on experience themselves. And now let me, yeah, so there is a question that it says there any threshold for the list of features so that we consider the variable as either significant or insignificant ones. So usually there are various other machine learning algorithms that actually decide whether a feature is to your problem is significant or insignificant. Principal component analysis is one of them, linear discriminant analysis, as well as some of the regression models. If you use like regularization techniques like lasso, you would be able to draw out the features that are not relevant to your problem or are insignificant. So how to decide whether you have data enough to start your first machine learning model? Yeah, that's a great question, and that totally depends on what you're trying to do, I guess. Like it's sort of, it could, generally speaking, the more data you have, the better your machine learning model will be. But essentially, cutting one particular set on where the data is enough, it's a golden question, and you'll have to kind of like start building your models and see if they're actually if they can be generalized to the data sets that it has not yet seen. Could you inform us if there is a possibility of a real-time classification algorithm being implemented online in DesignSafe workspace? Yeah, so the classification algorithm, that's a very general question that we are dealing with natural hazard, but in particular, we haven't provided any particular real-time classification algorithm as of now for any of these. I think some of the Sim Center might be doing some of these type of research, but I'm not quite sure. So I'm not quite sure on how to answer that. But as far as the DesignSafe, we have not do that, but it's a great idea depending on what sorts of a general problem is, and we can kind of like provide similar Python notebooks that handle these type of classification problems. Could DesignSafe team prepare a webinar about using MATLAB in Jupyter notebooks? Yeah, that's I guess Charlie, maybe we can think about that later to provide another webinar on how to use MATLAB in Jupyter notebooks. I'm not quite sure if that's if inside the Jupyter notebooks we can do MATLAB. At least I don't have the experience of doing that. Yeah. But
yeah, I don't think we have that available in Jupyter for DesignSafe yet. I will check with the DesignSafe team if that's something that they have in the pipeline or not. But I'm gonna shed a guess. I don't think so. Usually we just use matplotlib and Python to do our plotting in Jupyter. Seems to work a little bit better, a little bit easier to manage. But we do have MATLAB available as an application you can run through DesignSafe, but I don't think we have it available through a Jupyter notebook.
There is one other question as well that it says, how much of math background we require for using machine learning tools in natural hazard domain problem? And that's essentially, anyone can use machine learning tools in their field. However, the part that it gets tricky is the part where you will need to understand what it goes behind the scenes on these machine learning tools in order to have a meaningful model, because otherwise you will end up with a model that is, for example, overfitting or underfitting to your problem, and you will not even like understanding like why that is happening. A lot of hyperparameter tuning needs to be dealt with, like in terms of a decision tree, you will want to know like how much depth of a tree needs to be, how much depth the tree needs to go through, or if it needs actually a pruning type of methodology in order for you to get a good classifier or good model. So yeah, a little bit of understanding, at least it's definitely necessary for you to kind of like use these tools. But as far as the software side, it's very easy. As I mentioned, it's anyone with any little backgrounds in maybe coding can do that as well. Let's see. Is cross-validation necessary for random forest? What is size of the data to avoid overfitting? Cross-validation is necessary. I've actually had a slide in cross-validation. I just decided not to put that because it was going to be a little bit overwhelming as far as but yeah, it's gonna be one of the good ways to validate your model, to go through the cross-validation. Particularly for random forest algorithm. Can you recommend a good reference to learn more about machine learning for civil engineers?
Yeah, I just posted a link to an MIT Press book that I've used.
Okay, that's great. Yeah. Is there a rule of thumb to the choice of trees that you use for random forest regression? That's a good question. Well, I guess the important thing to note for that is to remember that inside the random forest, you're selecting your data points, a subset of your data points, and creating the trees from the subsets with replacements. So if you have like too many trees that are shallow, it's gonna perform as poorly as having few trees that are very deep. So you will have to kind of like go through the parameters that will tune your model best to go through that. Yeah, and at least I'm not quite sure on any particular rule of thumb for choice of like the numbers of the trees that you can use for random forest. Generally, the higher that you will select, your model is going to get more complex, and it's going to be more time consuming. So, and maybe like in the order of like 50 would be good for a high number of data points. So yeah, with that, please go ahead, try the notebook yourself. Let us know if you have any particular questions in the chat window.
Are there any other questions for Mayar? All right, I think we're good. Hey, thank you so much, Mayar, once again. Everyone, hope you all stay safe and have a great weekend. And we will see you all Monday. Thank you so much.
Thank you.